Hi, in this video, we are going to be going through the practice assessment questions and discuss how we actually obtain the answers that were given. In the first question, we are given a 3-bit ones complement number 101. Okay, so uh, a complement number, the sign bit is always represented by the most significant bit. So in this 3-bit number, the 1 at the most significant bit location is actually the sign bit. So we know this is actually a negative number. So to extend this to 8 bits, we just do a sign extension. So this will become 1111 over here. Okay, so this is the uh, ones complement 8-bit representation, and to make it a 2's complement, I add a 1. So I get 0, 1, 1, 1, and 1. Okay, so the answer is given here in part D here. Okay, so all I need to do is do a sign extension followed by add 1, okay, to get the answer. For question 2, we are given a base 16 hexadecimal value and I want to convert to base 8. Okay, so the first thing is I want to convert everything to the binary equivalent 1010 here, 1100, and 11110. Okay, once I convert it to the binary equivalent, the rest is to convert it to base 8. Base 8 is basically in groups of 3. Okay, so this will be one group, one group, one group, one group, and one group here. Okay, so there's a 1 over here. Okay, so after I split it up, I'll get 6 here, 1, 3, 5, 7, and 1. So the answer is B. Okay, so as long as you convert correctly and you start the octal conversion from the right hand side, the least significant bit, then you should get the correct answer for this. Okay, for 3, it's basically now we're doing it in the reverse than what we did in the tutorial. Okay, so given this representation and I'm supposed to come up with the actual decimal value. So the first thing is to convert it to the binary equivalent. So this will be 1100 0010 0010 0010 and all the way. Okay, so we know that in the IEEE 754 representation, this is actually the sign bit, so this is representing a negative sign. Now the remaining 8 bits here represent 132. Looking back at how we get this, we can say there is 127 plus the exponent gives me 132. So the exponent is 5. Okay, and then the fractional part, okay, is given by this. Okay, so what I need to do is, we know that we actually, if we look back at the steps, we need to normalize before we come to this. So the normalized version is 1.001 0010100, okay, multiplied by 2 to the power of the exponent, which is 5. Okay, so if I move this by 5 locations, 1 2 3 4 5, so this is the new decimal point. Okay, so this new decimal point gives this decimal part a value of 36, and this fractional part a value of 625. And since we know it's a negative number, it is negative 36.625, which is C. Okay, in question 4, basically we are having a printout, okay, of two numbers. This is a decimal integer value, so this will give me a value of 4. Okay, for the floating point value, dot 2f means 2 decimal points, so it is 7.97. 7.96623 will become 7.97. So the answer is 47.97. Okay, question 5 basically is about understanding what this type define does. Type define is basically a way of defining our new data type. So after I do this type define struct ABC and capital ABC, what I'm basically saying is struct ABC, small abc is equivalent to ABC. So they are both the same now. Okay, you can use type define for any type or any data type that you like, okay, to create your own name that you think that is more suitable or more applicable to that to whatever you are coding. Okay, so struct abc v1 is valid because you are creating a structure variable. This is basically an array of structures. So this is actually the issue, because struct capital ABC is equivalent to saying struct, okay, plus another struct ABC. Okay, so this will actually give you a compile error. So this is the issue. Capital ABC is equivalent to struct ABC, so it's 3 structure variables, and this is a structure array. Okay, uh, so an array of structures. Okay, so this is basically question 5. Problem, the statement which has an issue is statement C. Okay, question 6. Question 6 is about using a character pointer to point to a integer uh, data. Okay, so the way you can go about doing this is, before we do that, let's first have an understanding of what is meant by little Indian processor. Okay, given a data, okay, so if I give you this data 0x11223344, how do I represent this data in a memory? Okay, so we know that this is 4 bytes. Okay, so if I were to draw the memory, okay, so let me draw it side by side to, okay, and let me give some random addresses. So let's say this is the first lowest address, 8000, 8001, 8002, 8003. Okay, so this 4 byte data could be stored in two different ways. Either I can store it as 4433, 22, and 11, or it could be 11 here, 22, 33, and 44. Okay, so the one on the left where the least significant byte is stored in the lowest address, that is what we call a little Indian format. When you have the most significant byte in the lowest address, okay, then we call it a big Indian format. Okay, so these are just two different ways in which data can be stored in memory. Okay, and you need to know this if you are writing code or dealing with hardware devices at the memory level. Okay, so this is important information to know. Okay, so coming back to this question, so when I have 0x83 and a little Indian system, basically this is how it will be stored in memory. So the 83 will come here, followed by 000000. Okay, assuming this is the lowest address. So let's say this is 8000. So this is 8001, this is 8002, and this is 8003. Now, when I have a character pointer pointing to an integer, okay, so in the past we have seen integer pointer pointing to integer, or character pointer character pointing to a character. When I have a character pointer pointing to an integer, basically what happens is this line here, what it does is this pointer is assigned the address of A, and the address of A is a starting address, which is the lowest address of A. So pointer is now pointing to this. Okay. Now we are saying that we have a character pointer. Okay. In C by default, all data types are considered signed. Signed variables. Signed variables means they are represented in 2's complement form. The most significant bit is used to tell whether it's a positive representation or negative representation. So now the value here is x83, which is 10000011. Okay, but like I said, since this is a signed number, the most significant bit here tells me it's a negative number. So the actual value is obtained by doing a 2's complement. So 0111 1100, and I add a 1, so it's 0111 1101, and this is equivalent to 125. Since the most significant bit is a 1, so this means it is a negative 125. Okay, so this is basically how you interpret this question. uh, Generally, the important thing to understand is how we can actually use a character pointer to point to a multi-byte data, okay, and then extract information byte by byte. Okay, so this is actually a very useful trick that you can use when you want to just extract a single byte from a multi-byte data. Okay, using a character pointer to point to the integer or a double or anything. Okay. Okay, let's go to the next question. The next question is something similar. So again, this multi-byte data is going to be stored in this format here. So I have 443322 and 11. Okay, and character pointer here is going to point to here, the lowest address. Okay, so again, I'm just giving some random address only. Okay, it could be in any location, but we know that it is in consecutive locations. Okay, because it's a 4 byte data. Okay, so when I do a printout, what I'm doing is I'm printing out the value and incrementing the point. So after I print out the first value and increment the pointer, then increment the pointer and increment the pointer and so on. So I'm printing out 4, 4, 3, 3, 2, 2, 1, 1. So the answer is C. Okay, in question 8, basically what you have is you have an integer I with a value of 3 inside, and you have a pointer J, and it's holding the address of I. And after that, I increment J plus plus. So when I increment J, instead of pointing to I, I'm pointing to the address next to I. What is in this location, I do not know. Okay, because there is no variable assigned to this memory location. So I do not know what is here. So even though I do not know what is there, I can still print it out. Okay, so when I print it out, I will be getting some random unknown value. Okay, because I do not know what is inside that memory location. Okay, so that is the answer for question 8. Okay, question 9, basically you have an array num, character array. So the first element is 2, second element is 5, and I have two pointers. Okay, so this pointer value 1 is assigned to num0, so it's going to point to num0 here. So whatever is the address, so again, let's say this address is 8000, so this 8000 will come here, the address. And similarly, value 2 is pointing to the next location, and the next location in a character array is always 1 byte away. Okay, so what is important is the pointers are holding the addresses. Only when I say asterisk value 1 and asterisk value 2, I'm pointing to the data. So when I take value 2 minus value 1, I'm taking the content currently inside the pointer, which is the address of this element and this element, and the difference between two elements, two consecutive elements in a character array is always going to be 1. Okay, so the answer here is 1. Okay, in question 9, basically we are just trying to play around with the base address of the array. As we know, the starting address of any array uh, is equivalent to the name of the array. So just using the name of the array is equivalent to the address of the starting element. Okay, so rightfully, okay, this is your array 0, this is your array 1, and this is your array 2. Okay, but now what have I done? When I say array plus 1, I have shifted my starting point by one element. So this becomes my new array 0, this becomes my new array 1, and this becomes my new array 2. Okay, so when I print array plus 1, 2, I'm actually printing out 4. Okay, so this is just manipulating the starting address, okay, of the array, okay, and assigning it to or sort of using a new starting point for the array in the code. Okay, so the next question here is fairly easy. Given number 8, shift left by 1 is 16, shift right by 1 is 4, and actual number is 8. Okay, so 11 is B, 16 for 8. Okay, so that wraps up the C programming part. For question 12, basically a jump instruction. For instruction, all we need to know is the address of this label. So the address of the label is given as X4000. Okay, so if this is the address, all I need to do is first write it out in full hexadecimal representation. So this is only the lower 16 bits. Okay, so I need to write out the full 32 bits here. Okay. And once I write out, basically in MIPS encoding, what I need to do is to remove the upper 4 bits, remove the lower 2 bits, take this entire address and put the opcode in front. And the opcode is 000, 000 Okay. And after that, I can convert to the hexadecimal equivalent, and that'll give me an answer which is E. Okay, so I'll not go through the details again. You can try this out. Okay, question 13 is a standard MIPS encoding question. I think the only thing to note is the -5 is represented in 2's complement. Okay, as long as you take note of that, you should be able to get the correct answer of A. Okay, so again, I won't go through the details of this. It's fairly similar to our tutorial question. Okay, question 14 is asking us to load a value, okay, of 1, 1, 2, 2, 3, 3, and 4, 4 into our register. Okay, so looking at the instructions, we should know that A and B is not allowed because we cannot put a 32-bit immediate value inside the instruction like add I or RI. But load immediate is possible because load immediate is a pseudo instruction. Okay, again, this may vary from assessment to assessment. For this practice assessment, if you look at the front cover, I have already explicitly stated that all pseudo instructions are allowed, okay, unless otherwise stated. So load immediate, which is a pseudo instruction, is actually allowed. Okay, in question 15, basically the first one is given that the starting address of the array 1 is this, what is the address of array 2? So array 2 starts after array 1 ends. Okay, so we need to know how much memory array 1 occupies. So this is a word array, so each of this element is 4 bytes. So 4 bytes means total of 16 bytes, which is equivalent to 0x10. So I take 0x10, add with this, I will get the answer as D. Okay, so that is the starting point of array 2. Okay, right after array 1. Okay, the next question is asking why is the value stored in register T4 at the end of the program. Okay, so if you examine the code, basically what is happening is S1 is pointing to the array 1, the first element here. So I'm going to load, okay, so these are the registers T1, T2, T3 and T4. Okay, and T1 is having a value of O1, O2, O3 and O4. So that is the first four instructions here. And then these three instructions, what do these three instructions do? Shift left. So what happens is T4, I'm just going to show you for one, the rest you can see for yourself. T4 is having a value of 4. After I shift left by 24, so the upper bits are all 0. And after I shift left by 24, what happens is T4 has a value of 04 over here. Okay. And similarly 3, after I shift left by 16, what I have is 0003 0000. T2 after I shift left by 8, I have 00000200. And T1 I'm not doing anything, so T1 has the original value of 00000001. So and here I'm doing an OR operation. So after I do an OR operation here, okay, I do an OR, what I have is 04030201. Okay, that is written back to T4. Written in T4 at the end of the program. So that is your question 16. Question 17, basically what does it do? So S1 is holding the starting address of value, which is the first element. Take the first element with offset 0, means the first full word, and load it into T1. Okay, so T1 is having a value of FFAA1122, and I copy that into T2. So T2 has a value which is the same, AA1122. And then what do? I do a shift right operation of T1. Okay, so if I do a shift right operation of T1 by 16, so I'm shifting everything by 16, so 0000 FFAA. Here is your T1. And your T2, what am I doing? I'm doing an AND with FFFF. So I have 00001122. Okay, and after that I'm doing a shift left by 16. So after that T2, when I shift left by 16, I get 11220000. And the last instruction is I'm going to do an OR. So I do an OR between this and this. I get 1122 FFAA. Okay, which is your 17. Okay, now the next question. Okay, so in this question, we are basically examining load byte and load byte unsigned. Okay, so S1 is pointing to this word here. And as I said just now, when I load the address, I'm always going to point to the least significant byte, which is this. Okay, so when I load offset 1, I'm going to load this element here. Okay, because I'm doing a load byte. Okay, so a load byte, the offset of 1 will be CD. Okay, so if I look at T1, okay, T1 is going to have a value of CD over here, and T2 is also going to have a value of CD over there. But what's the difference is this instruction is a load byte, this is a load byte unsigned. In a load byte, after I load the byte, I must do a sign extension. And since C is 1100, I'll do a sign extension, so it will look like this. Okay, whereas T2 is a load byte unsigned, which means it will look like this. You only have zeros in front. Okay, which means that if I try to do a BQ, I will say that it is not equal, so the branch will not be taken. Okay, so this is again a comparison between the load byte and load byte unsigned instructions. If you have not examined these instructions in your class or what, then you do not need to be worried too much about it. Okay, question 19 is quite straightforward. It's just basically looking at the BEQ instruction and the control signals that you need. So if you're looking back at your notes, you know that a BEQ instruction is a register destination of X, register write of 0, and branch of 1. Okay, so that is quite straightforward. Okay, question 20 is we are looking at the branch. Okay, so we know that rightfully the branch as an AND gate. So you suppose have a branch control signal and the is 0, and then you have a PC source here. But now you have made a mistake and PC source is directly tied to is 0. Okay, and we are given this sequence of instructions. Okay, so if you look at this sequence of instructions, we can see that S1 points to this word, so it points to the lower address. So if I look at what are the value in T1, T1 is having 55, okay, T2 is having AA, T3 is having 55, and T4 is having AA. Okay, so when I say if line 6 has this instruction, branch is equal T1 with T3, okay, both of them are equal. So BEQ instruction will actually do a subtraction. So a subtraction will, or 55 and 55 will give you a 0. So the is0 will be set. So if the is0 will be set, then based on the current design, I will make the processor take the branch. Okay, so the answer is yes, the branch will be taken. Okay, how about the next question? The next question says, what if the instruction was AND T3, T4, and put into T5? So let's look at T3 and T4. T3 and T4 are both 55 and 88. Okay, so 55, okay, which is 0101, 0101, and AA 1010, 1010. Okay, so when I load these two inside, what will happen? So we know that for load byte instruction, I will do a sign extension. Though this will all be zeros, and this will all be ones. Okay, so when I do an AND of this, what will happen? You can see that it's all alternating ones and zeros over here, and all zeros and all ones. So eventually everything will be a 0. Okay, so as long as the answer is 0, the is0 will be set. So the answer is yes, the branch will still be taken. Okay, so because of the mistake in the processor design, an AND instruction can also cause a branch to be taken. Okay, question 22, we see another mistake. So rightfully, we have two control signal, register destination, register write. But in this case, register write is tied to register destination. Okay, and we are asked to examine which of these instructions will always execute without wrongly updating any of the registers. Okay, so that is the key thing. So what we need to do is we need to analyze the register destination and the register write requirements for each of these type of instructions. Okay, so for the first one, add instruction, we know that the register destination is always here, which means it's supposed to be 1. Okay, and this always updates the register, so register is also always 1. Okay, so in that case, you can see that since both of them are the same and both of them are 1, this instruction will always execute correctly. Okay, no problem. For a load word, what do you know? For a load word, this is actually the destination. Okay, the RT location. So the register destination is supposed to be a 0. But a load word instruction requires an update to the register, so the register write is supposed to be a 1. So in this case, there is a mismatch. Okay, they're not the same, so this is not going to work. For store word and BEQ, both we know that register write is going to be 0 for both of these instructions. And we also know that for both of these instructions, the register destination is going to be X. So since both of them are X, it could be a 1 or could be a 0. Okay, so which means that if it's 1, okay, then there could be a issue. So we know that based on this, only instruction 1, okay, is able to execute correctly without wrongly updating any of the registers, okay, because if this happens to be 1, and since register destination is tied to register right, I may accidentally write, okay, so this happens to be a 1, then I may accidentally write the register, okay, so that is why stalwart and BEQ are also potential hazards here, okay. So only the add instruction is able to ensure that it will still carry on executing correctly without wrongly updating any of the registers. Okay, in question 23, we are looking at the timing analysis. I will not go through the whole sequence here, but from our tutorial, we know that RTA instruction like add will take 980 picoseconds. A load word instructions 1300 picoseconds, and the branch instruction is 800 picoseconds. And we are asked to find out what is the possible frequency. Okay, so let's look at it very simply. The fastest that you can go depends on the slowest instruction, and we know that this is the slowest instruction. Okay, so for this slowest instruction, what is the frequency? So 1300 picoseconds, if I take a reciprocal, it's approximately 770 megahertz. That means this is the fastest at which I can clock the processor, and since I cannot go any higher than this, I can only take an option that is smaller than this. So the only possible option is 700 megahertz. Okay, so the answer is A. For 24, okay, the basic idea is we have redesigned the adder block within the ALU. So within the ALU, the adder has now been improved, okay, to make it much more efficient. Now the question is, which of the following type of instructions will always see an improvement? Okay, for R type instructions, we have arithmetic, plus we also have logical. So yes, arithmetic will see an improvement, but logical will not see any improvement, okay, because the adder does not come into play here. So not all R type instructions are going to improve. For load word, there is always an addition because there is always an offset with the base. So that will always improve. And a BEQ will always improve because a BEQ is a subtraction. And a subtraction is addition of the complement. So this will also improve. So the answer is D, options B and C. Okay, so the last, again, this may not be have been covered in class, but basically just to give you an idea, MIPS processor is slightly open-ended in a sense. You don't have to stick to a Little Indian format. You can have MIPS processors that are both operating on Little Indian format, and you can have MIPS processors operating on Big Indian format as well. Okay, so the answer to this is false. Okay, so that wraps up the review of the practice assessment questions. So I hope this gives you a better understanding of how we derive at the answers. Okay, so thank you and good luck.